8.3 lesson. So this is probably going to take a good number of notes here. Coulomb's law is something that they will test on, not by name, though you don't actually have to know the name. They might mention it, but you don't have to know the name. They don't ask questions like, what is Coulomb's law? Remember, this is a high-level test. It's a high-concept test. They expect you to apply the principles in this equation. They don't actually ask you to calculate anything, though. So that's not minus F. This should be more like colon. It's just F equals. Now, K is just a constant. I don't even know what it is. Q is the charge for some reason. I know we use small q in another context. Sorry. And D is just distance. So what this says is that the charge between ionic particles is proportional to the charge between them and inversely proportional to the square of the distance between them. Basically, as the charge between them goes up, the force between them goes up, and they are more tightly bound to each other and harder to pull apart. As the distance decreases, they get more attracted to each other and are harder to pull apart. The force increases. So smaller distance is more force and more charge is more force. And that's what they're going to test on. The core electrons are the ones in the inner shells, not the valence shells, whatever's inside the valence shells. The valence electrons, of course, are in the highest or outermost shell. The nuclear charge is Z. That's the number of protons in the nucleus. And what they're talking about is something like if you had N714, this is the A number and this is the Z number. So that's why they called it the Z number, because that's the number of protons. I don't know who made them A and Z, but there you go. So the effective nuclear charge, or Z effective, or ZF, I guess, is the charge felt by the outer electrons. So let's do an example for nitrogen. The ZF would be 7 protons minus the core electrons. Now for nitrogen, the core electrons is only 2 because it's only using level 1 as the inner shell. Its outer shell is shell 2. The 5 valence are in shell 2, so it has 7 total electrons, but only 2 of them are not in the valence shell, are below the valence shell. So we get 7 protons minus 2 inner electrons, and the effective Z charge, or Z effective, is 5. So what we find then is that the effective number here would be 3, 4, 5, 6, 7, 8. And the shielding, the blocking of the nuclear charge, or the sort of electromagnetic pull by the protons, has been blocked less and less and less. So the Z effective is effectively the pull on the valence electrons by the nucleus. And as you go across a period to the right, that number gets greater, illustrating that the pull from the nucleus to the valence electrons gets greater, which means, big point here, these get smaller as you go across a period, across a row to the right. The atoms tend to get smaller. So helium is very small. Ionization energy is the energy required to remove an electron from an atom. And so we were talking about how the pull from the nucleus to the valence electrons gets greater and greater and greater as you go across here, and also lesser as you go down, we should note. That means that the ionization energy is getting greater as these get smaller. And we said it gets lesser going down. That means it gets greater going up. So ionization energy increases up and right. You have to use more energy to pull an electron off, more up here and less down here. So these two go together very well. Electron affinity is the energy released when an electron is added to an atom, which goes right along with how much an atom wants an electron. Those two will both increase again up and right, with the note that the noble gases don't have an electron affinity or an electronegativity because they don't have any need for your dumb electron. They're great with the way they are. They're happy if we can pretend that they have emotions. They have a completed valence shell, and they don't want your dumb electron, and they have no use for it. And in fact, if you look at electronegativity tables, they just simply don't even appear. So a family is a group or a column of vertical column on the periodic table. So here's column 1. And as you go down the table, kind of the whole point is that you keep getting S1, S1, S1. The protons, of course, increase as you go down a column. The number of core electrons, of course, increases. But look at this, the effective pull, the ZF, is the same. And that's also kind of our point with the way the periodic table is laid out. However, as you go down a column, the sizes get bigger. And this is the distance from the center of the nucleus to, I think it's the point where the electrons spend 90% of their time. Anyway, you won't be tested on that. And by the way, PM is picometers, which is a trillionth of a meter. Yeah, you thought nanometers was small. Well, picometers is 1,000 times smaller than that. But atoms are very small. And the ionization energies get less and less and less. Like we said, as you go down the table, the size gets bigger and bigger. The valence electrons are held on less and less, and it gets easier to pick them off. You have to spend less energy to pick one off. The ionization energy goes down. Let's talk about row 3 here, going to the right. We've already talked about how to do electron configuration. The number of protons, of course, is increasing by 1. The number of core electrons, though, stays the same because they all have shell 1 and 2 as their inner electrons. They're not valence electrons, so everybody has a 10. But since the number of protons is going up each time, we get 11 minus 10 is 1, 12 minus 10 is 2, etc. So as I said, the effective pull from the nucleus on the valence electrons is getting greater, which means these are getting smaller, as we see here. Now, the ionization energy tends to get greater and greater and greater with a bit of a hiccup, as we see in this graph. So why would there be the hiccup in this graph? And they do get to test on this. One of their favorites is nitrogen and phosphorus to ask about. Now, aluminum requires actually a little less energy to pull an electron off, because if you pull an electron off, what you get is going from 3s2, 3p1 to 3s2, and that is a filled subshell. That's the S subshell filled, and that's actually a bit of a point of stability. So it's easier to pull this one off than that one. That would be ruining the completed subshell, whereas pulling the first electron off silicon would not be ruining a completed subshell, and it would not be creating a completed subshell. Again, pulling one electron off aluminum would be creating a completed subshell, and nature kind of likes that. So it's actually easier to do that. You're giving nature kind of what it wants. And the same kind of thing applies here in a bit of a different way. If you pull one electron off of sulfur, what you get is 3s2, 3p3, and that is a half-filled subshell. What you get there is 3p3, which is 3 orbitals with 1 electron each. See my previous video. They do not clump up together if they can help it. And this is another point of stability. So if you pull an electron off of sulfur, you've created something nature likes, which is a half-filled subshell, or 1 electron in each orbital, same thing. And so it's easier to pull an electron off of sulfur than it is off phosphorus. It's easier to pull one off oxygen than it is nitrogen. This same kind of hiccup repeats across periods. Which is bigger, K versus Cl? Well, K is using shell 4 for its valence. Cl is using shell 3, so K is larger. Now, here's another trick that does come up sometimes. Which is bigger, chlorine charge 0 or Cl minus 1? This has added an electron, but of course no more protons, and that makes the electron cloud bulge out wider, so it has a larger radius. So a general trend here is anions are bigger than charge 0, and conversely, by the same reverse logic, cations are smaller because you've removed electrons but not changed the nucleus. So the same protons are able to pull on fewer electrons, which pulls them in tighter. Now, another kind of trick question is, which is bigger here? Potassium loses 1 electron and effectively lands on box 18. Chlorine gains 1 electron and effectively lands on box 18. So they both have 18 electrons, but potassium has 19 protons to pull them in with, And so it is smaller. It does a better job of pulling them in. Cl minus has a larger radius than K plus. For this table, I'm going to show you the periodic table. So I would get this out and then follow along on the periodic table. What I can tell you about the ionization energies for boron is this. Removing this electron is, of course, going to be the easiest because it's the outermost one. And there's going to be a real noticeable jump between removing electron 1 as opposed to electron 2, okay? So the first one comes off, and that's not so bad, not so hard, because when you remove the first electron, you create a situation where you have a completed subshell as the rest of the main subshell. There's nothing else in the valence shell except this completed subshell, and that's a point of stability. Nature kind of likes that. So the jump between removing electron 1 and electron 2 is going to be really noticeable. Removing electron 2 ruins that situation of having the completed subshell. So that's going to be definitely more energy required. Then this is going to be less because and it's definitely going to be more than that one. Now the big jump though comes between removing electron 3 and electron 4, because when I remove electron 3, I create a situation of having a completed main energy level. And nature likes that. So this is going to be easier than that one by a lot. And that is on the test. They expect you to be able to identify the column that an element is in by identifying the big jumps. Look for the big jump in ionization energy, and that's the transition from one period, one row, down to the next one. So if we look at this graph again, we can get a visual representation of the ionization energies. Now, it's probably not going to be represented in a graph, but they give you values. So if the answer was supposed to be silicon or a column 4 element like carbon, then the pattern would go, we have some starting ionization energy for the outermost. Then it gets a little bit easier because that's creating the situation where I just have the completed S subshell. So that gets harder. Removing this one even gets harder, then easier, and then there's going to be a big jump. This is going to turn out to be much easier than removing the next one. So electron 1, 2, 3, 4, if there's a big jump between removing electron 4 and electron 5, you know that that was the transition. Go wrapping back around the periodic table, and in this case, that would be wrapping around from element number 11 box to element number 10 box, and we would have been positioned 4 boxes beyond that, so you would be talking about either carbon or silicon. On 8.3 problems, we have this table of ionization energies, and I can't really do a lot with row 1 and row 4 without a lot more information, but look at the huge jumps from the first to the second ionization energies here and the second to the third, and that tells me this is sodium and magnesium. They did say it was period 3 there, and that's because there's going to be the biggest jump when I cross from box 11 to box 10. And in this case, removing the second electron was much harder than removing the first. So removing the first here was much easier than removing the second. Nature likes to have a completed subshell. It's going to fight you if you want to remove the electron at this position, whereas removing this one is not going to be so hard. In row 3, it took the removal of 2 electrons before you get to the huge jump. So that tells me I'm probably at the magnesium box, or anyway, the column 2 element, or anyway, the column 2 element, and they told me it was in period 3. So that's magnesium. For this one, go grab a periodic table. For this one, go grab a periodic table. Calcium, having lost 2 electrons, lands on box 18. So does Cl, having gained 1 electron. But the calcium has more protons to pull in the electrons, and so but the calcium has more protons to pull the electrons in with, and so it's smaller. Metals are less electronegative or more electropositive. Sure. And lead is in the same column, sure, as carbon, but it's dealing with a valence. Lead is in the same column as carbon, sure, but it's dealing with a valence shell of 6 instead of 2. So those electrons are much more easily pushed around. And that means that you can push electrons through a bunch of lead much, much easier than just a bunch of carbon. On D, pulling the first electron off of boron is going to be a little bit easier because when you do that, you're creating a valence shell that has a completed subshell, subshell S. Go grab a periodic table and see what I mean. You move from box 5 to box 4, and that's actually going to be easier than moving from box 4 to box 3. They don't ask stuff like this anymore. I'm going to skip it.